Hi, I'm Bob Dobkin. I'm Vice President and CTO at Linear Technology, and I'm going to be talking about the LT4180. We call it a virtual remote sense device. It's a device that's made to work with existing power supplies to improve the regulation. If I have a power supply and I have line resistance to my load, no matter how good I make this power supply, I still have bad regulation of my load. And if I have bad regulation of my load may not work properly. So there have been ways to improve this, and the most common way is to use remote sensing. Here we run an extra pair of wires from the power supply over to the load. And the extra wires actually sense the voltage at the load and allow the power supply to correct for it. Typically, the correction range is pretty small, just a couple of volts. And there's downsides for having extra wires. One, it's harder to hook up. It can get hooked up wrong, and when that happens, depending on the supply, you end up letting the smoke out of the supply and you have to go get another one. There's labor and there's cost involved. It would be nice to keep the voltage right at the load, independent of what the load current is and what the resistance is, without any extra wires. And that's the magic part. That's what the 4180 does. The LT4180 is designed to work with most existing power supply circuits. It'll work with switching regulators, linear regulators, it'll work with silver boxes, it'll work with isolated power supplies driving an opto. It's a complete control circuit that implements the virtual remote sense. Now, virtual remote sense is an open loop correction for line drops. And we do that by measuring the line drop and correcting for it with the LT4180. The way we do that, the magic part, is we interrogate what the line resistance is at a pretty high frequency, anywhere between a few hundred hertz and 8 kilohertz. We have several sample and holds in the 4180 that hold voltages and currents at different times. The cycle works like this. We first have a voltage control cycle that sets our output voltage. Then we hold that output voltage, and the voltage control loop is disconnected, and we have a current control loop that's connected in. The current control loop controls the current flowing from the power supply to the load, and we modulate that current by 10%. So we have a delta I of 10%. We then go back to the voltage control loop and correct the voltage using the information we gained from the delta I. Let's suppose I have a delta I of 10%. I have a delta V at the output of my supply of 10% of my line drop. Because I have a big capacitor at the far end and I have an AC zero impedance here, all of the voltage change is due to the line drop. So I take that 10% of my voltage, I amplify it up, I sample it, hold it, and I correct my output voltage with it. So within a few cycles, the output voltage gets corrected for the amount of line drop we have. And that's independent of the line resistance and independent of the load current. It always works right. What happens if the capacitor gets disconnected? We don't have any signal, or the load wires get disconnected. So we don't have an error. So by using this computational technique, we can get an improvement in our load regulation. How good is it? We can get between 20 and 50 times better regulation using this than without it. This is the output of a power supply that is nominally set to 5 volts. This is the voltage drop to the load here. It can go up to 2.5 volts. So that's 50% of my power supply output. Here's the voltage that my load sees, the voltage change my load sees as my output, my line drop goes up to 2.5 volts. I only lose 80 millivolts at my load. So on a 5-volt supply, an 80 millivolt regulation is just over 1.5%, so it's not a problem. But if I had a 2.5 volt change at my load, that would be a problem for almost anything designed to work on 5 volts. Here's a scope photo of what the output looks like on the 4180. This is my load current, jumps up to 600 milliamps. This is the output of the supply, and that jump is the correction voltage due to the line drop. The fuzz on this waveform is the interrogation signal, and this is running at about 8 kilohertz. This is the voltage across the load. The fuzz is taken out by the output cap that's across the load. And here we see some small transients on the output as a function of the load step. If the transients are too big, you can make the output capacitor bigger. The bigger the output capacitor, the lower your transients at the load end, and the lower the noise. So we correct for the line drop, which in this case is 1.2 volts, down to a negligible value. Where is this good for? Any place where you have fairly long lines going to your load. Powering something over Ethernet, a couple of 100 meters out, you can correct for 50% of your voltage drop down the line, maybe some more. If you have remote items like hotspots or remote lamps or other types of devices where the voltage control is important at the load, virtual remote sense will keep your voltage correct at the load. One particular application is incandescent lamp power. Halogens are still pretty prevalent, being used for high intensity lighting. And like any incandescents, they're very, very voltage sensitive. The lifetime goes down as the 16th power of the voltage. But when you're using them for light, the amount of light goes down much faster than the power goes down. So if I have a 12 volt bulb and I'm running at 11 volts, my light output is about 30% down, and my power output is less than 15% down. So it gets a lot less efficient in terms of converting power to light as the voltage goes down. So if your voltage isn't right, you're going to need more bulbs for a certain lumen level. Well, that's another application where a virtual remote sense power supply could make a lot of sense, because you'll keep the voltage on the bulbs correct. You'll need fewer bulbs, and for a certain lumen level, you'll need less power. And the LT4180 will do that. Now take a look at an actual circuit. This is a linear regulator, but as I mentioned earlier, this could be a switching regulator, an isolated regulator, or all kinds of different devices. Here, the 4180 is the actual control loop. Don't have another control loop. We have a pass FET for our regulation. We have our 4 sample and hold capacitors and a frequency compensation capacitor for the sample and hold and the loops in there. We have frequency compensation for the regulation loop, our current sense. So this is a complete virtual remote sense regulator. And as you can see, it's not particularly complicated, and it does things that you can't do any other way. We've done a lot of work on this regulator to make it easier for you. We have application notes, data sheets, SPICE models, and they're all waiting for you at www.linear.com. Thank you for listening.